Chapter 17, Lecture 2. In this lecture, we actually talked about buffers, and or in the previous lecture, we talked about buffers, and we decided to leave this example problem for Lecture 2 as a review of the idea of buffers. Recall that buffers contain both a weak acid and its conjugate pair. So it's a weak acid conjugate pair. And because you have both an acid and a base, conjugate, you should say base pair. You have both an acid and a base, a buffer can handle any strong acid and any strong base, neutralize them, and then keep the pH roughly steady, is the idea. So here we're asked about how many moles of NH4Cl must be added to 2 liters of 0.10 molar NH3 to form a buffer whose pH is 9. So what this requires us to do, let's go ahead and clear it, is to use the buffer equation and to solve for one of the mole values in the buffer equation. And recall that the buffer equation takes this form: pH is pKa plus log of base over acid. And the buffer equation essentially comes from the icebox. This is a kind of a shorthand or a shortcut, you can say, to the icebox. And remember, these are molarities, but you can use molarities or moles here. Either one. Moles actually will be the preferred use of the unit. So what we're asked, we're given 9 for the pH. So we're saying pH is 9.00. Now, the pKa, we can just determine the Ka of NH4+, and the way to do it is to go from NH3, because it turns out we have the Kb for NH3 in the back of the book, and that's 1.8 times 10 to the negative 5th, and if we recall, Ka is simply Kw over Kb, so if you have the constant of the weak base, you can derive the constant of the weak acid by simply dividing. So let's get that. We got 1.0 e negative 14 is Kw, divided by Kb in this instance is 1.8 e negative 5. And we should get ourselves, go ahead and compute that. And we should get ourselves 5.56 e negative 10. This is our Ka. We'll need the Ka in order to solve this equation, because recall this P means the negative log of, just like the P in pH means negative log of H. So we got ourselves negative log of 5.56 10 to the negative 10th plus log of, now our base is actually 0.10 molar, and our acid is the unknown. We're asked about the conjugate acid, so this guy here is actually the acid, the unknown. That's what we'll be solving for, the NH4+. So what we can do is we can either use molarity, the 0.10, or we can directly use the moles. Because eventually we'll be asking about the moles, why not we use the moles directly? Go ahead and convert from molarity to moles, and if you recall, molarity times liters gives you moles. Moles, which means we get 0.10 times 2.0, which gets us 0.20 moles. So here is how much we have of the base. So the base goes up here, we get 0.2, and the acid is our unknown. That is what we'll be solving for. So notice what we've done here is we've simply set up the buffer equation and plugged all the values given into the buffer equation, and now it's a matter of solving for the denominator here. This will be a bit tricky. You'll actually have to undo, you'll have to unwrap the log. And if you know anything about this, you'll have to raise everything to the 10th, or 10 to the power. So go ahead and compute this real quick. Let's go ahead and compute this. Take the negative log of 5.56 e negative 10, just to clean it up a little bit. which gives you 9.255 plus log of 0.20 over the acid, and these have to be bracketed like this, equals 9.0. Let's go ahead and move this 9.25 over to the left side by subtracting, and that will give us negative 0.255 will equal log of base 0.20 over our acid. Really, the rest of this is algebra, and what we're doing here is algebra, but it is a bit involved because we're using logs. So if you recall, the way to get rid of logs is to raise 10 to that power. Raise 10 to that power, this gets rid of, because our log is base 10, that gets rid of the log. So if you do 10 raised to the power of 0.255, negative 0.255, you should get yourself 0.556 will equal 0.20 divided by your acid. So to solve for the acid, I'm going to multiply the acid out this way and divide the number down this way. And your amount of acid will equal 0.20 over 0.556, or 0.36 moles. So the problem was a bit involved. Really, it came down to plugging everything into the buffer equation and solving for an unknown. We're using the buffer equation. Anytime you want to prepare a buffer so that you can keep the pH of a solution steady for your chemical needs, you would have to decide and calculate how much of the acid or base needs to be added together to prepare that buffer. And this is kind of a review of using the buffer equation. We're going to do a few more slides for this lesson, and actually first let's talk about the idea, a little more in depth about the idea of a buffer. Let's consider something called the buffer pH range, and this is the range of pH values over which a buffer system works effectively. So it turns out buffers, if you want a buffer, say that buffers a pH of 5, you have to use a special set of chemicals to create this, versus if you want to have a buffer that buffers at a pH of 12, you'll use different chemicals, and that's what this is talking about. And the way to do this is you use an acid with a pKa close to the desired pH. The buffer equation looks like this: pH equals pKa plus log of base over acid. So what you want to do is you'll have equal amounts of base and acid, whatever this number is. If you have 10 moles of base, 10 moles of acid, this drops into 1, and the log of 1 is actually 0. So this whole thing drops out, becomes a 0, and you get the pH equal to pKa, and that's why this makes sense. The example here is if you have acetic acid's pKa is 4.7, and again, to get this, you would negative log its Ka, which is 1.8 e negative 5. You get 4.7, and so acetic acid can buffer a solution around a pH of 5. So it's not practical to use any old chemical to create a buffer at 5. It's really practical to use acetic acid to do this. And we're actually going to do an example or two using this concept here. So here's what we'll do. Anytime you have a buffer, and if you add a strong acid or base to the buffer, the base portion will neutralize the added acid, forming a bunch more conjugate base, and the acid portion will neutralize the added base, say sodium hydroxide or something, forming that much more conjugate acid. And here's kind of the diagram, and this may be a bit confusing. We'll have to work it out a few times, but here you have your buffer containing both the original acid and its conjugate base. Then we decide to add some strong acid. Going this way, the strong acid gets neutralized by the base portion of the buffer. But in turn, because anytime you neutralize a base, a weak base, you will form a bunch of that conjugate acid. So what we'll have to do essentially is recalculate how much acid and base we have after we've added. And likewise, if you add a strong base, hydroxide here is a strong base, the acid portion will get involved to neutralize that strong base, and in turn it will form more of the conjugate as well. And we'll have to recalculate our amounts and then plug it into the buffer equation. So, and we'll have to use the buffer equation here then. So there'll be two steps here. The first step is we'll have to do some stoichiometry calculations as promised. Every chapter will involve a stoichiometry type problem, so that's exactly what we're doing here. And then we'll use our equilibrium idea. Really, we're going to use the buffer equation to find the concentrations at the end. So let's try this. Actually, before we try it, here is another overview of the same exact thing. So when solving buffer neutralization problems, number one, these are going to be the two steps we just outlined above. We would have to determine how the neutralization reaction affects both the weak acid portion of the buffer and its conjugate base portion. And then, step two, as we've discussed, plug this into the buffer equation. So if we begin, here's a visual, if we begin with equal amounts of both the acid and the conjugate base, and we decide to add some base, notice what happens. The acid portion gets neutralized. We go from 0.3, subtract 0.02, down to 0.28. But at the same time, we're adding that much conjugate base. So we have new amounts. Then we can plug the buffer equation, plug these values into the buffer equation, and we got a pH. Notice the original pH was 4.74. The pH went up slightly. It's still around 5. The pH is still kept steady, but it just goes up slightly. If we do the same thing by adding acid, the base portion of the buffer disappears. So now we're down to 0.28, and the acid portion increases. We're up to 0.320. And then we recalculate again using the buffer equation and find the pH being roughly at 5 still. So we'll finish up with this problem. This problem will be a bit involved, so why don't we take a look at it and see if we can make some sense. We have ourselves a buffer made by adding this many moles of acetic acid and this many moles of acetate. This is the same buffer we did calculations for in the previous lesson. And we add enough just to make a liter of solution. The pH of the starting buffer is 4.74. And we would like to know, A, what happens to the pH of the buffer after we add 0.020 moles of sodium hydroxide, and B, what happens if we add another 0.030 moles of HCl to the buffer. Okay, so our buffer equation will be the second step. The first step is stoichiometry. Stoichiometry means our buffer will have to get neutralized and the amounts will have to change. So we're beginning with what we can do, what I suggest actually here is setting up a type of icebox. We won't call it the icebox. Why don't we call it something else? Let's go and clear it. If you take a look, so here is our acid and base pair. O2 minus. Let's call this the begin, change, and end box. This is essentially like the icebox because the icebox also deals with stoichiometry, except we'll call this the BCE box, not the icebox. What we're doing here is we're calculating how much we're going to lose and how much we're going to gain. We're beginning with 0.300 moles of our acid and 0.300 moles of our conjugate base, which is usually the case. You usually begin with equal amounts of both. And then we're adding, in part A, let's do part A first, we are adding some NaOH. Now NaOH is a strong base, so when the strong base comes into the buffer, it will reduce how much acid we have. So what we'll do is we'll subtract 0.020. Now as we subtract 0.020 here, based on stoichiometry, this means we have to add the same amount, 0.020 here. And we end up with 0.320 and 0.280. Let's try that again. Here. And then these are the amounts we'll put into the buffer equation, the HH equation. So notice what we've done. This begin, change, end box is analogous to the ice box, except here we're undergoing neutralization. And what we'll have to do then is calculate this H+, and that's what the buffer equation helps us do. So the buffer equation says that the pH is equal to negative log of Ka plus log of base over acid. And the base and acid should be either molarity or moles. Let's go and plug the values in. Our negative log of Ka, we calculated our Ka earlier for acetic acid to be 1.8 times 10 to the negative fifth. So let's go ahead and do the negative log of that value. 1.8 e negative fifth plus log of our base. Now this is our base, it's our conjugate base. So this value will actually go on top. So we got 0.320 divided by 0.280, as that is our acid. Here, this amount, remember, this is our original acid, and it's acid base over acid. So go ahead and plug and chug. This is a matter of plugging it in. I'll give you a minute to compute this and see if we come up with an answer. I would suggest computing the ratio here first. 0.320 divided by 0.280. Compute that, take the log of that, and then add that to your negative log. And see if you come up with the value. So let's try that again here. Take the log of this value, it gives you 0.05799. A negative log of that value gives you 4.74. Add these two together and you get yourself 4.8. Notice our pH went up slightly from 4.74 up to 4.8, which means our buffer is working effectively. So this is from adding a little bit of base. How about if we add a little bit of acid? So what we'll have to do, and we'll do this on the next page, these are our starting amounts, and then these will be what we begin with, and then we'll do the same thing. So 0.280 and 0.320. So we had our equation looking like this. Dissociating our acid, dissociating into H+, and the conjugate base, C2H3O2 minus. We got the begin, change, and the ending box. BCE instead of ICE. And so we began, if you recall, with 0.280 and 0.320. Now for the change, it says that we are adding another 0.030 moles of our acid, a strong acid, HCl. Now the strong acid will actually be neutralized by the base, so 0.030 we'll have to subtract from here, so 0.030, because as the acid is added, the base, remember this is the conjugate base, the base is what neutralizes the acid, means the base disappears, but because of stoichiometry, we add the exact same amount of acid back to the reactant side. So in the end, this gives us 0.290, and this gives us 0.310. Let's go ahead and plug this back into our HH equation, and we'll solve for the new pH. And HH equation again says that the pH is equal to the negative log of our Ka plus the log of base over acid. So we can plug this in. Negative log of 1.8 times 10 to the negative fifth was our Ka, plus log, in this case our base is 0.290. Our acid is 0.310. Go ahead and put this into your calculator and see if what you find out. This is still 4.74 plus that ratio logged. And this should be this should be negative 0.02896, and it is negative because this ratio is less than 1. Anytime the ratio is a small number, the logs are negative, because the power of a tiny number is negative. If you think of a tiny number like 0.001, the power of this is 10 to the negative third, and that's why we got a negative number, because remember, this is what the log button does. It undoes this power. So we ended up adding 4.74 to that, and this gives us 4.71 for our pH at the end. Notice the buffer still works around 5 pH. That's what it's buffering, roughly 5 pH. So in part B here, we added a strong acid. The base was able to neutralize the strong acid. In part A, we added a strong base, and the buffer was able to neutralize the base. And this is the power of a buffer. So we'll do a few more of these in class, but this for us concludes lesson 2 of chapter 17.